first of all, thanks a lot. Thanks to Dimitri, to Jacobi, to Nelson for the invitation and to talk to you and have nice discussion, this nice environment and nice building. And I will try to be short because there are people that are craving for barbecue and I don't want to spoil your night. Okay. So I'll talk about this curious feature of infrared QED that some work I have done some years ago, but with Balachandra, Secik, and this name is complicated, so I will skip. Kyrkosjöglu. And no, Secik in Kyrkosjöglu in Sachin Vaidya, and there are some, it is interesting because it's associated with the construction of charge on, of QED. And it has got some momentum because of the recent work of Strominger, Hawking, and Perry. Although the difference, of course, I will be doing in special infinite and their work on light-like infinity. So. But there are some interesting stuff. It's not that much connected, but the ideas are similar. So just to recap some basic stuff, Maxwell theory, we have the usual, I want to construct just charge, so just the usual stuff. So usual Lagrangian for Maxwell equations. So I want to construct a Hamiltonian of electromagnetism, then I fix some spatial slice, and then construct the Lagrangian. I do the usual textbook constraint analysis by Dirac, which gives me the Hamiltonian, the square of electromagnetic fields plus the square of magnetic field, with the canonical Poisson bracket, where A is my coordinate and the electromagnetic field, it's conjugate momenta, and I get Gauss law as a constraint, a first order constraint, which I can write this, just a weakly equal value on the constraint surface and all that. But we also learned that in quantum field theory, fields are operator value distribution. That means that I have to be a little bit more careful in treating this constraint. So I have to smear it with some test function, because E is a distribution. So and there is this derivative. So I choose some test function, which is the gauge parameter. And this is a proper way to write the constraint, the Gauss law constraint. And because of differentiability, which very simply means that I want to perform partial integration, get rid of the boundary term, I have to demand that this gauge parameter, the test function, goes to 0 as I approach the boundary of my space. In this case, I consider the boundary at infinity. Say it again, please, louder. I'll come to that, just wait. I'm defining now pure gauge. So the pure gauge, this is the only possibility. When I will introduce the charge in the next slide, then I will allow it to be different. I will choose, so I'm differentiating two classes of test functions. One will account for the pure gauge or small gauge transformation, and the other are the charge and large gauge transformations. And this is the crucial thing I'm doing here. So thanks a lot. Going on, so I have this G of lambda, which is this functional, depend on my gauge parameter, which generates as all first class constraint, the Lie algebra of my U1, which is my gauge group. So this defines for me, because of this boundary condition, the small gauge transformation, and this satisfies the U1 Lie algebra, And my field should transform as a derivative of the parameter, and the electric field is invariant under this transformation. Of course, upon quantization, I want that G lambda, it will annihilate any sensible quantum vector state. So that's what we learn in school. Now, charge, differently, charge is defined as this equation, which is EI of the derivative of some test function. But now, I demand that the test function goes to a constant when it approaches the boundary of my space. So this defines for me what I call large gauge transformation, the large E1 gauge transformation. These are different of what previously in previous slide where I was defined as small gauge transformation or pure gauge transformations. Of course, this charge, the usual definition of charge in electromagnetism, it should be invariant under small gauge transformations. Okay, that is that. Now, so this is usual stuff. Now, I have some motivations to change the class of the parameters, the class of test function I'm going to choose for the definition of the charge. And this, one of my initial motivation was the following. Because of infrared, photons come from far from the past, it accumulates in some special slice. And usually, if I want to set up some initial data condition for my dynamics, I have to take into account what I will put in this special slice. So, but this soft photon come from the past, it will start to accumulate. So in order to define my Cauchy problem, I have to try to model it properly, this cloud of infrared photons in my special slice. So, and I do that because there will be some accumulation of these infrared photons at special infinite. Here's a figure or a cartoon, if you like, of this is my special slice where I want to put my Cauchy data for my differential equations to evolve. But there will be photons come from the past, and the farther in the past, it will start to accumulate. So, because of this motivation, for instance, I could say there is photon come from CMB or some fancy thing like that. That is my motivation to change the way I'll model my test function of my gauge parameters. Of course, I could, there are other motivations as the sheer construction of charge at infinite and the possibility of construct infinite charge at infinity, resembling a little bit what is done, for instance, in gravity, which is the special infinity group called the SPI group by Stecker, or if you do it in light-like infinity, it will be the, in gravity, it will be the BMS group. And nowadays, for instance, there are some nice papers by Strominger where he constructed this light-like charge at infinite for QED itself. So, but I mean, the difference here, I'm doing a special infinity. So this would be some additional motivation to do that. Here, so the proper description of this cloud of infrared photons, I could consider some direction-dependent gauge transformations. So I will consider my parameter, my test function, to depend on the direction in the sky. Now, this will provide for me a bigger gauge group, and the name, we call it Sky Group. Just a nice name coined by Balachandra because it will come some infrared coming from like a CMB, which is a sky, and it resembles this SPI group of Stecker. So, and because before I had only one charge, now I have an infinite charge, as we constructed in the next slide. So the number of generators of this group, this sky group, has infinite number of generators. Huh? I will show it to you. From here. Let's suppose when usually I will set up the Cauchy data for my in this Kovalevskaya theorem. I have to set up the values of my fields in some compact region, right? Now, the way I will do that in this compact region can be impact from the past, from some photons come and imprinting some values on this thing. Okay, then I fix that. But now, I can go towards the past longer. So I have to enlarge my compact region, take more regions. Also saying it is starting to accumulate in the boundaries of my compact region here. If I fix here, then it starts to have some accumulation here. If I take photons come from faster and faster, something like that. Okay, so the question, so I have to model the gauge parameter, this test function that enters in the definition of the charge, what I was called it chi. So, but now, before chi was a constant, and it should define only one generator of the U1 group, large U1 group. But now I allow chi at the boundary to be dependent on the angle, let's say theta and phi. So if I expand these values with in spherical harmonics in the sky, the sphere at sky, then I can expand this. Then I have all this QLM, and each of these QLM will set one generators for my sky group. Since I have an infinite of this generator, now I have the algebra of charge will get enlarged. For instance, if I only consider electric field of a point charge, then I only have the monopole, and then I have only one generator. I terminate this expansion at the first order, zeroth order, if you like. Of the sphere at infinity. Yeah, this is what this is what I'm saying. The difference is that the Ströming is doing in light-like infinity, null infinity. I'm discussing this as special infinity. Chi0n is some arbitrary function that depends only on theta and phi. Theta and phi. Some, yeah, this is some direction in a sphere. So usually use theta and phi to define directions. It's not constant. It's a function. See, if it is a monopole, it comes from a monopole, then I will have only Q00. This will be constant. This chi naught theta phi, maybe I should write it like that. It's confusing. These are spherical angles. That is so it's arbitrary function. I have not specified it yet. So, of course, if it is a constant, which is one possibility, then I go back to the previous situation. Okay? For instance, of course, if for instance, in the case of an electric field of a point charge. Now, I can also consider radiation field, for instance, some charged road going up to infinite, then I have also other option here, or some dipole and things like that. So that is, I think it's now clear that I'm defining a different set of charges for generators of this charge group. So the charge of the sky group consists of an infinite set of quantum numbers associated with those generators. So instead of only Q00, which is the regular, the usual charge, I have this tower of charge. So a quantum vector state now should be labeled by all these quantum numbers. Not only the dynamical ones, but then I have this set to define my charge. What do you mean gauge connected? What do you mean by gauge connected? Kai. No, only if it goes to 0. Here I'm not allowed it to go. So this is the first set, what I'm called G. In this case, I'm splitting two kinds of gauge transformations. What I'm calling pure gauge transformations, or small gauge transformations, that are defined by this kind of set test functions that goes to 0 in the boundary, so it doesn't reach the. This defines a class of gauge transformation. Now there is another class of gauge transformations that are defined when my test function, it is a, there is no, I'm not talking about instanton. I'm not talking about instanton. I'm talking about charts. There is no instanton here. It's just a plain Maxwell theory. Yes, perfect. This is a very good explanation. I like it, very good, in a context which is in principle more complicated. But I mean, this is simpler than this context. I mean, for instance, in Brown and No case, that is what Daniel is explaining. No, I also separate what is a small gauge transformation, large gauge transformation. The large gauge transformation are those that change, let's say, the boundaries at infinite, and then change the charge, and the charges are the Virasoro algebra defined by the Virasoro generators. But here is I mean, at least in my opinion, it's simpler. See, but for instance, in the Maxwell theory, there will be only one generator at infinity. But now I'm allowing, because there is, as far as I know, no physical principle that forces me to fix this gauge transformation to take only one value at my boundary. So since there is not this principle, I will try to explore all the possibilities. Is it that okay? Can you please? Huh? Usual gauge transform generated by the first class constraints. Gauss law. Charge. Gauge field. Field is here. Here. This is a gauge transformation, as you learn, here. See, this is my field, and how it changed by G of lambda. Here, let's start all over again. Okay, this is a Lagrangian for Maxwell equation. I'm fix a slice, construct a Hamiltonian. I get this canonical Poisson transform, and then the Gauss law. That's okay? Thanks a lot. We, in a sense, we learn. We learn this in school. If you open up NO Teitelbaum book of 1670s, or if you do as he's proposing ADS 3, Brown and O, well, I mean, if you do Gupta Bloyer, I think, I yeah, I'm trying to bring this stuff to main stage so that we can change a little bit. But for instance, what we learn in school is that charge is defined as the flux that across some closed surface, Gauss surface. Oh, this pretty much is the same I'm doing here. But what you mean that the flux is being crossed at this surface? So I have to say what happens to these test functions, right, at the boundary. The only difference here is that I put the boundary at infinity. So my charge is what of the electric flux is reaching infinity. This is charge.
We are trying to distribute some charges.
Good, yes, perfect. I mean, I may be careful to use perfect, but George is not here, is there? I will avoid using perfect. Okay. So this is back then I define my charge. So here is the tower of charge. Now I have, because I'm distributing this charge over infinity, so I have to label my quantum vector state by these guys, this QLM, all this set, infinite set. And here the gauge, pure gauge, it annihilates it as it should be for a constraint. And these are the generators of charge that just measure the charge according to its angular momentum numbers. Now, this set defines what we call superselection sector, but if you like, it defines what we call a vacuum. Okay, this is just a vacuum, or some irreducible representation of the algebra of a local observable. The reason I'm calling it superselection sector is that there is no local observable, some observable that I define in a compact region that are able to change this set. Once I fix the set, it's fixed in my theory, for these local operators. Okay? But again, this is similar to what we learn when I have only one charge. Okay? If I want to change the value of this charge, like in Dirac, change the quantization, no, charge is some integer of the monopole, of one over monopole. If I change it, no, there is no local operator that changes it. So this integer that defines the charge, they are superselection sectors that define my theory. Okay. So there is no local observable, then that is. Now, but then what I would like, something I skip? No, okay. So, but if I want to define the Poincare group, the Poincare group is defined as an integral over all the space of my generators. So it involves the integration of local fields, as this is Weinberg's book, of the whole spatial slice. So it's a global symmetry. Different of what I was doing so far with the local symmetry, is this global symmetry. The question is, are such global symmetry implementable in the given irreducible representation of the algebra of observer? What I want to say is that, is this global transformation preserving my set of charts, or are those global transformations changing the set of charts and therefore changing the vacuum of my theory? Okay, that's my question. If it changes, then I say that this global symmetry is spontaneously broken. Okay? Otherwise, it is the usual stuff. Let's see an example. For instance, I have for SU3, I have 2 reps, the 3 and 3 bar. Otherwise, I would not have we are talking about QCD all the time, no? So I have 3 and 3 bars. But now, the conjugation symmetry, it changed from this irreducible representation to this, to another irreducible representation. So this conjugation symmetry is spontaneously broken. Okay. Similarly, for the case of U1 charge, which was the first situation, Poincare is implementable. Of course, we know the usual QED works well. There is no spontaneously broken. So, but now, because Poincare Group is the integral of some local fields and it defines over all my space, I can have a rotation generated by the Poincare Group, by some part of the Lorentz group, that rotates my sky, my boundary. So by doing that, it starts to change these charts. So it starts to shuffle this starter in a precise way, of course, according to the transformation. So it changes the vacuum, or changes the super-selection set. Therefore, Poincare is not implementable by the in this sky group, and then it's spontaneously broken. So it doesn't happen if I have only one chart. Okay? Of course, you can say this is a reason to just throw this theory in the garbage, but that's okay. I was trying, but then that's life. Huh?
What are the corresponding ones to the bottom?
That is, no, I have not construct, sorry, but that's a good question. No. It should be some construct. I mean, what are you construct next will be some coherent state. You can call them a gold stone, but since it was not a simple, I will refrain to use this, but maybe you're right. Okay. Okay, so I will construct a vertex operator. So the vector operator are those operators that change this set of charts from one set of charts to another set of charts. This is and they should be invariant under small gauge transformation generated the pure gauge transformations. So, for instance, if this cat is a general vector carrying the trivial representation of the sky group, when all those sets of charges set to 0, or has only the Q00 at 0, this I would dub the trivial representation of the sky group. Now, what the vertex operator it does, it change this this vacuum, let's say, this set of charts from what I'm calling 0 to some omega. This is just a nickname for those this set here. Okay. So this is what a vertex operator does. It's the same as what a vector operator does in strings in conformal field theory. Yeah, it changes the charge at infinity. Good. Yes. So, and for it should be invariant under small gauge transformations. Now, with respect to the large gauge transformation generated by the charge, I should obtain some Y-like algebra. Y-like because I have my charge, I have my vertex operator. If I try to commute them, it will appear some central term, and this central term, it depends on the parameter of my large gauge transformation and the set of charge that I'm using. Okay. This is just some formalities, but I can try to be a little bit more precise and realize them. For instance, one possible realization is that I will model that set of charts by this omega. If you wanted to consider omega some goldstone, some omega at the sphere at infinite, and it is a closed form. And then I define my the vertex operator by the exponential of this integral here. Because it should be this condition of invariance of with respect to a small gauge transformation, then because of some commutation here, this G acts pure gauges, right? It changes A to A plus d lambda. If I insert it back here, and do some partial integration, I see it to be 0 because the omega is a closed form. Just some way of modeling this. Good question. I can take omega like that. This using, instead of that realization here, I use this realization here, which is this is a vertex operator. But now I'm using this, instead of omega, I change a little bit, not a little bit, a lot of the notation from omega to theta. And here is the Chern-Simons. So the Chern-Simons appear in the realization of my vertex operator. And then I can check that my Weil algebra is fulfilled. And I observe that this, for instance, for this trivial representation, which there is no charge, it is respected by U, but then this W, as we expect from some Chern-Simons transformation, it changes the vacuum, just like theta vacuum.
You talk now about states, but is it not that it's in fact a classical phenomenon? Nothing is quantum?
It's quantum. It's quantum. No, quantum because I turn all of that. See, all of these become operators. All right, if it so.
Suppose I want to consider classical operators.
You,
They will realize the same infinity many generators as infinity.
no, but then my algebra here will not be like that. No, I will not. It will be. This will be commutative. Then yeah. I think you can do that in classical level, but then I will have a different algebras and a little bit different with especially this Y-like. I don't know if I will have it. Most probably, but no, you're right. Okay. Okay. I can do it in any dimension, but I'm doing a 4-dimension. I can do in any dimension. Here I'm doing 4-dimension. Then I have a 3-dimensional slice with spatial slice. That's why the Chern-Simon in 3-dimension. But yes, you can do it in classical. I have not done so. I mean, but well, after all, the world is quantum, so perfect. But okay. So this realization, I mean, in terms of the Chern-Simon, is nice because you can. It's easier to do a generalization into a non-abelian gauge groups and things like that. Okay. Actually, we have studied that already, but I will not put any slide about that, where we discuss some vortex construction, this vertex operator constructing vortex. Then there is some relation between the vortex created by that and the charge, so the duality vortex charge. Okay, but that was a different kind of game. Now, I now what I want to do is to study the effect of these, if let's say that this kind of charge exists, so what will be the phenomenological effect, or if it is somehow measurable? Of course, I will not give any numbers, but just to see what we can get from physics in that. And this can be done in the following way. This is, I can bring the effect of the vertex operator to my Maxwell Hamiltonian or to the Lagrangian, and therefore, no? Then, and this will correct the mass of the fermions, coupled with electromagnetic field. This is the same thing as Et Hooft did with theta vacuum in the 70s, when he brings the theta effect from the kinetic term and put it in the mass, coupling the mass of the fermions, just creating this topological mass. At least I learned it from Et Hooft, so I don't know if in the papers, no? So the effect then, how it goes, very simple. The effect of the vertex operator of the electric field, let's suppose I have in a states that are labeled by this omega, which are a set of those charges. So E, the electric field, so I know that a V omega construct relates omega vacuum to 0. So this is, I can insert in this. And now, this conjugation of EI, the electric field by the vertex operator, just in first approximation, I can get this correction to the electric field, parameterized by my vacuum, or superselection sector label, which is omega. Then this means that, I mean, the B field do not be changed, but, and then the Hamiltonian in the sector, in the omega sector, in this other vacuum, will have this form, where I correct the electric field by this extra term here. If I want to consider a Lagrangian for this Hamiltonian, the Lagrangian will have a term like that, which is a topological term, F mu omega whole sigma. You mentioned that I could associate with F, indeed. Okay, no, it's you, sorry. Okay, so it's the same thing that we do as with theta vacuum in QCD. The difference now, I have this F field, and omega is a field characterized my infrared cloud. Okay, so if you like, it's a BF, kind of a BF theory. Now, so I can take the effect of in the kinetic term to the mass if I couple this theory with fermions, then I can change the mass of these fermions. This is the bare mass of my fermion, but then it should be correct by this cloud of charge, by the usual construction, as you do in the theta vacuum. Okay, so it will appear this term here. The one way of modeling this omega, which is this infrared cloud, was done by Fröhlich and Strock and Mork on this in the back 7, so it's old stuff. So, and they used this to compute this QED in Coulomb gauge, which is a nightmare. Okay, but I mean, it was done. We can use some of their results. So the outcome is that the change of the mass will affect the form factors that I need to compute. If, for instance, I compute the G factor of the electron, it should be changed. And of course, electric and magnetic polar momenta will be changed. Actually, all of this computation I have already done in the past for this, and compute what is the effect of this kind of change for the EDM computation. So since there will be changes, just like in the EDM, the computation are pretty much the same, so the scattering amplitudes will be affected by the change of these fermion masses. only the external, only the on-shell fermions will be changed because of it's only a change in the mass. And so the mass gets stressed, but in very short, without much being so fancy, the dispersion relation of those fermions are changing. So it now depends on the charge, but depends also on the momentum of the fermion that is taken. Okay, so it is the mass gets it's get dressed by this infrared photon. Because of this change, it must depend on that. We can compute. Yeah, it's associated. Yeah, this is the same reason. So you just see that it's the same as saying that the Poincare is being broken. This is here, let's say, a realization of explicit realization of this fact that Poincare is being broken spontaneously. Okay, and so that is the idea. Just now to finish, we have also done a concrete computation when I have for the charges of the dipole type. So there is just Q00, Q1 minus 1, Q10, Q11 minus. So if I only consider this for my test functions or my parameters defined in my charge, we can really do actual computation. It's quite boring and complicated. I took some days to do that, but anyway, you get this form here. What this effect does to mention, it's boring, but I mean, it's the usual exercise of when we compute the infrared divergence of in QED. So these infrared divergence are cancelled by the soft photons. So it is the same kind of computation. Okay. Anyway, so the twist mass, since it depends on the momentum, as I showed the previous, is not a scalar under rotations, and I mean it. Now very simple to see that it will affect the decay rates and some scattering particles of some particles in this medium. That is to say, for instance, it happens that if I see a muon come from sky in this direction, and I compute and I observe the decay, its time, its lifetime, and in this other direction, it will be different because of this effect. So in principle, it could be measured and see that actually the universe will have this kind of charge defined in my sky. Anyway, but up to what you know experiment today, there is no such effect, but we try to see if it is there. Okay, it is not. We know that Lorentz symmetry is a good symmetry. Ok, so muito obrigado.